Now that we've talked about each of Maxwell's equations individually, we can talk about them as a group and their important consequence, electromagnetic waves. Now, there's an important thing that I need to tell you about before we start, and that is an addition to Ampere's law. Ampere's law bonus. And that is called displacement current. What that is normally Ampere's law, the way that you just learned it, was that the curl of H is equal to, capital J, equal to J. That's true if there's no time-varying stuff, but when there is time-varying stuff, we get an additional term. And that term is plus the time derivative of the electric flux density. This term is called the displacement current. Interestingly, this is why capacitors don't always look like a short circuit. This is why there can be current flowing in both sides of a capacitor even though there's no physical path for it to go through. This displacement current is what makes everything work. And it's also what makes Maxwell's equations work. This was Maxwell's big contribution to the theory of electromagnetics too. Besides just writing the equations down, it was this term that took us from magnetic fields have this weird response, have this weird time-varying magnetic flux gives us this weird voltage behavior to, time-varying fields in general are linked to each other and we have electromagnetic waves now. So, let's write down Maxwell's equations, and I'm going to write them in phasor domain. And I want to remind you that in phasor domain, the time derivative has an interesting behavior. So if you have some phasor quantity, let's say it's that, if we move to the phasor domain, that just becomes a multiplicative factor of j omega on the same quantity. And that is because the time derivative of e to the j omega t is j omega e to the j omega t. And none of the other components of this expression have any time dependence. So with that in mind, let's write down Maxwell's equations. We still have that the divergence of the electric flux density is the volume charge density. We have Faraday's law over here, so the curl of the electric field is minus j omega mu h. Remember that mu h is B, and this minus j omega right here, that's a minus time derivative. So that's minus d dt. We have that the divergence of the magnetic flux density is still 0 even in phasor domain. We have Ampere's law, now with displacement current. So we've got J, these are source currents, plus j omega epsilon E, that's our displacement current term, plus sigma E, and that's conduction currents in lossy media. So in this situation, the volume charge density here and this current here, those are sources. We're going to think right now about how waves propagate through areas where there are not any sources. So we're going to assume a source-free region. In which case, we're going to ignore that rho v term, we're going to ignore that j term. This is true anytime we're not physically right on top of these sources. So even if we're right next to them, if there is not a source directly at the point that we're considering, we are in a source-free region, so it's fine. The currents and charge distributions can still exist, but they're a consequence of the fields that are present. So there are things like this sigma E term, that's okay. So what I'm going to do is I'm going to derive the electromagnetic wave equation from these Maxwell's equations. And the first step to that is to pick either Faraday's law or Ampere's law and take the curl of it and then substitute the other one in. I'm going to pick Faraday's law. So I'm going to do curl of E is equal to curl of minus j omega mu h. Now we're assuming that this is a homogeneous medium, so that means that mu is not varying with position. That's material parameters don't vary. Which means that this curl really only operates on the h term here. So now we have curl of E, and we're going to simplify that in a minute, is equal to minus j omega mu curl of h. Well, look at Ampere's law, which we helpfully have not yet scrolled past. We already have a term that involves curl of h. Curl of h, we can substitute in all of this stuff that depends on E, and then we can eliminate h and have an equation just in terms of the electric field. That's great. So, rewriting that, curl of E is now minus j omega mu sigma plus j omega epsilon E. That's looking good. Let's simplify that double curl now. The double curl, we know from a vector identity that curl of E is equal to the gradient of the divergence of E minus the Laplacian of E. So let's put that up in there. Oh, and there's one other important fact that we need to know here, and that is, since we're in a source-free region, that means that there's no volume charge density. That means that the divergence of D is 0. So that means that the divergence of the electric field is also 0, because we don't have anything fancy going on with the electric permittivity. So now our new wave equation is minus Laplacian of E is equal to minus j omega mu times sigma plus j omega epsilon E. Or if we multiply it out and move some things around, we end up with Laplacian of E, whoops, plus j omega mu sigma plus j omega epsilon E, like that, equals 0. Now take a look at this. This is a wave equation because it's got second derivatives with respect to position, and second derivatives with respect to time because we're multiplying these two factors of j omega. So that's 2 time derivatives. So that is the electromagnetic wave equation. You can do the same thing starting with Ampere's law instead of starting with Faraday's law, and you get the same result except with E replaced by H. So you can write the same equation for H like this. That's also fine. I have a sign error right there. When I moved over that Laplacian, I flipped a sign. So that should be a minus sign, and that should be a minus sign. My apologies.